This is a normal image texture of a ground. It has color information of the ground, and it has flat and uniform lighting. The fact that it does not look real is quite obvious, but what can we do about it? Well, we simply need to add more information about the material properties that are important for correct light interaction and adding a realistic look. We can deliver this information with other image textures that provide data about the physical material's properties and characteristics to simulate its real behavior and appearance. These types of textures are called physically based materials, also known as PBR materials, and they are used in the 3D industry for games, animation, sci-fi art, movies, and other sectors where realism is a must. Now, PBR materials come with various maps because every material is different and has different properties and characteristics. So I will show the most common maps, what physical properties they simulate on the material, why they are used, and by the end of the video you should have a general overview of what PBR materials are and how you can use them to make better renders. The first map is the color map. It represents the diffuse or base color of the material without any other integrated lighting data, such as shadows or reflections. For instance, if you're texturing a wooden surface, the color map would exclude all cast shadows between the cracks, maintaining only the surface's color and texture. This is important because you don't want baked shadows or reflections in your materials, since we want to display shadows based on the light source location and direction in our scene. Also, color maps are one of the few that use RGB color space because they need to show the color properties of the material. With that being said, it should always be connected to the color input, which is usually the first input in any shader. A metallic or metalness map is used to simulate metallic materials, and as the name suggests, it should be used for rendering metals because metals interact with light slightly differently than dielectric materials like plastic, wood, or paper. Metal maps are likewise grayscale, but it's preferable to stick to white and black values because the fact that a surface is metallic or not is often binary. When the metallic value is set to its maximum, the material appears darker because fully metallic surfaces reflect their surroundings more, and the albedo color becomes less visible. When metalness reaches 1, the surface loses practically all of its albedo color and just reflects the environment. If you decide to use this map, make sure it is connected to metallic input and the color space is set to non-color. Let's talk about how roughness works. The roughness map shows how rough or smooth the surface is. Besides that, this map also controls the sharpness of reflections on the surface from the environment. A rough surface scatters light in multiple directions, resulting in diffuse reflections and softer highlights, while a smooth surface reflects light more directly, creating sharp highlights and glossy reflections. Again, the value range on this map goes from 0 to 1, where 0 represents a perfectly smooth surface with crisp reflections, and 1 indicates a very rough surface with diffuse reflections. To put things into perspective, a rubber has a roughness of about 1.0 because it absorbs almost all light that hits the surface, whereas a mirror has a roughness of about 0 because it reflects almost 100% of all light with minimal scattering. Again, make sure to switch the color space to non-color. Let's talk about normal maps. Normal maps are useful for providing fake depth without the cost of additional geometry. They simulate the way light interacts with the surface using complicated computations to create smaller bumps and dents. This way you can simulate rough surfaces with real-time light interactions by using only one single image texture. For this reason, normal maps are often used in game assets because using one normal map is computationally cheaper than using extra geometry to make the details pop out. Notice how these maps visually differ from others. Unlike roughness or ambient occlusion maps, normal maps are light purple, meaning they use color data, where each RGB value represents a different axis or direction in the 3D space. These values are used to simulate the way light interacts with the surface of an object, creating the illusion of depth and intricate surface details without increasing the actual geometry of the 3D model. Again, make sure to switch the color space to non-color, and the map is connected to the normal map and then into the shader's normal socket. Now let's talk about how to actually displace geometry by using a height map. A height map, also known as a displacement map, is a black and white texture that contains elevation data for physically accurate microdisplacement. A height map is a type of grayscale map in which black represents the mesh's bottom and white represents the mesh's highest peaks, with shades of gray indicating everything in between, meaning the brighter areas represent more elevation and the darker areas represent less elevation. It looks very similar to a roughness map, so be careful, they can be easily confused. The benefit of height maps is the amount of detail they offer, which appears perfect from every angle and under any lighting condition. The downside of using height maps for displacement is that the quality is limited by the amount geometry your object has. Therefore, the more geometry you have, the more detailed the displacement will be, which also increases render time. A height map can also be converted into a bump, so it can be an alternative option for a normal map. If you want to use displacement in Blender, you need to plug the height map into the displacement node's height socket, and then plug the output into displacement. And to actually see the displacement, you need to enable displacement in bump under settings in material properties. Alpha is quite easy to understand because it uses black and white values to drive the material opacity. In simple words, it works as a mask, and it tells the shader which areas are transparent and which are opaque. Black areas refer to 0 opacity and full transparency, and white areas refer to 100% opacity and 0 transparency. It can be used for decals, leaves, and other non-uniformed objects like flames, branches, and more. Transparent PBR materials and decals often come with separate image textures, but if you are adding a PNG image with a transparent background, you need to plug the alpha output of that image texture into the alpha socket, and you need to switch the blend mode to some of these options. Now let me tell you something about emission maps. Emission maps cause some elements of your material to radiate their own light, allowing them to be seen in dark places. Meaning, with an emissive map, the material has the ability to emit light by simulating the emission of light by the material itself. Emissive maps are color maps used to define the color of the light emitted by a material. When a material is set to be emissive, it emits light independently of other light sources in the scene, adding a self-illuminating effect to the object. These are also full RGB maps, and they're similar to an albedo map, but they're for light. The emissive color map should be connected to the emission color. Now, with this in mind, let me show you how you can actually apply all these maps to your object in Blender. First of all, you need to download PBR Material. There are a lot of free online libraries offering them with CC0 licenses, and if you don't know about any, I made a list of websites where you can find and download these materials for free. Next, unpack the file, copy the path, and open Blender. Go to Add-ins and enable Node Wrangler. Now select the object you want to texture and add a new material. Then press Ctrl-Shift-T and find the folder with the material. Here we have all the necessary information for the shader to properly display the material as realistically as possible. Select all of them and click on the blue Setup button. Blender will automatically read the textures and connect them to the principled BSDF in the correct order. Now, some of the maps, like ambient occlusion, are not connected automatically because there is no slot for this map. So to correctly set up ambient occlusion, add a color mix node, set the blend mode to multiply, first connect the color map, then connect the ambient occlusion, and then connect the color output to the color actor again. If you want to make the material more wet, for example, add a color ramp between the roughness and the principled BSDF and slide the black values to add more reflection. For the normal map, it is recommended to lower its strength because it is too intense. If you want to see the displacement, you need to be in cycles, and you need to go to material properties and under settings. Change the displacement setting to displacement or displacement in bump. And finally, for the displacement node, you should lower the strength because, again, by default, the displacement will be set to 1, which is too intense. Now you know what PBR materials are, what they do, how they work, and how to set up and import them into a Blender. If you found this video useful, consider subscribing to Graffinity and sharing this video with someone else who might find it useful as well. By the way, check out this video, and with that being said, see you next time.